Hello and welcome to this workshop on how to predict multiple time series at once with Scikit-Learn in 10 simple steps. Here we will do a sales forecast case study. Sales forecast is probably the most popular time series forecasting task that we have. So I believe it is not only that, but a good way for you to understand how to apply this to time series. This is a very direct, very straightforward tutorial, and my goal here is that you leave this presentation, leave this workshop able to apply immediately everything you learn here to the time series that you are trying to model, to the time series that you are trying to predict. It's very, very practical. My name is Mario, and thank you for being here. Let's begin. So the first thing, of course, we have to import some libraries. So we are using pandas, NumPy. Here I have matplotlib. Basically, I always import these three libraries, but the two additional libraries that we are going to use here are the Scikit-Learn, the imputation module, because we will have to deal with some missing values. And the other one is the random forest from the Scikit-Learn ensemble module, which we will use as a machine learning model. So the first step here is we need to melt the data and stack the series. So many people think that when you have multiple time series, the only way for you to model is actually to create an individual model for each of the series. And then let's say if you have 10,000 products, you actually need to have 10,000 different models, each predicting a single product that you have in your store. But this is not the case. Actually, creating a single machine learning model has some advantages, like you can capture some more global effects, you have more data to train, which usually helps the model to learn better the patterns that you have. And actually, you have a much easier time maintaining this in production. You have to deploy and keep only one model working, so your pipeline is much simpler. And usually this actually gives you better performance. We are using the sales transactions dataset weekly from UCI. You can see the link below. But here we have about 800 products. And originally this dataset has a column with the product code, 52 columns with the raw weekly value of the sales for each product, and other 52 columns with the normalized weekly sales values. Here we are only going to use both the product code and the weekly values, the raw weekly values of the sales. So to put this into the right format for us to use with machine learning, we have to melt this data. Melting this data simply means that we are going to transform each of these rows and columns into each row will have a product code, a week indicator column telling us which week we are working on, and a third column that will have the actual value of the sales that correspond to that week. So we are filtering here just because of this, just to get the columns that we need, and this is what our data looks like in this first step. Then we actually do the melting. Pandas has a very, very easy way to do this. We use this function data.melt. We have the pd.melt too, but it is the same thing. So we put the identification var, so which column has the entity that we are trying to predict. So here we have the product code is our identification we want to predict for each product on each week. The variable name that we want, let's say each current column name to have. So we have each week in a column, what is the name that we want this new column to have that will get all these previously column values. And we have to set up a name for the value column of what we are trying to organize. So here, I think looking at it, it's much simpler. We actually get that format that I was talking about. We have the product, we have the week, and we have the sales. This is a row-wise, let's say, format. This is the ideal format for machine learning, at least traditional machine learning, the one that you find in Scikit-Learn, and it's the one that we are going to use here. If your data is already in this format, you have to do nothing. You just need to stack all the data together. So let's say that you have a product 1, product 2, but these are different files or different databases. So you just have to concatenate all of them together into a single data frame in this format. So the basic idea is product code or entity, whatever it is. If it's the stocks, for example, what is the stock symbol? The date, in our case, it's the week, and the value that you are trying to predict. Very, very simple. So another step that we have to do for this data set is that our product code had a letter, it was a string. So here I'm just transforming it to a digit because originally I was using this product code to encode the type of product. You don't necessarily need to have a categorical variable indicating the product or the entity that you are modeling, but you can use it. Here we will not use it. We will depend only on the features that we will extract from the series so that we can have a more general model, but nothing is wrong with you putting more features, more variables than, let's say, the product code, or for example, if you have the product title, you could use some text variable. It's not a problem. And then we have the week. Again, we have W0, W1, so we will extract only the numbers that we have just to make it easier for us to sort, to use this data. And then I like to sort the values by week and product code, because when we do some group bys in the next cells, it will be easier. We don't have to resort the data every time that we need to compute a feature. So I like to already have the data sorted so that I can just do some simple computations to get the features, get the data that I need transformed. So this is our current state of data after the transformations. We have product code, week, sales, but now without the letters. So the second step here is splitting the data. I always like to split the data before I start modeling or doing some more complex transformations, because this reduces a lot the risk of some data leakage, of computing some feature that actually I will not have in production. So here in the second step, we are going to split the data into training and validation. When we are dealing with time series, it's very important that we don't split randomly. Random split is wrong when we are talking about time series. I have read many papers. I have tried a lot of time series validation methods. I even made a Portuguese language course about it. So when I tell you the worst thing that you can do is the simple validation split, the random validation split for time series, please trust me. So here we have a very simple but very effective way of splitting the data, which is just selecting a point that separates the past from the future. So we have to simulate the future in the validation. So we will get, in this case, we have 52 weeks. I will get everything before the 40th. I don't know, I'm not a native English language speaker, so week 40. So everything before week 40 will be our training data. Everything containing week 40 and forward will be our validation data. And you can tell me, but Mario, don't we need a test data? And we could have a test data here. I decided to not have it, to not overcomplicate this tutorial. And one thing that I have seen, the more I work with machine learning in practice, is that the true test is always in real data in production. This does not mean that you will publish this, you deploy this model, and actually people will start making decisions before you evaluate, but the real test for your model will be when you actually set it to create the pipeline to get the data in real time, or get the data when you actually deploy it, when you actually set up the pipeline to get new data, do the predictions, and then you can compare the real performance of your model. So I don't see the point of getting too concerned about having a test set. And the other thing is it's very, very difficult to tragically overfit the validation set when you are tuning the model or something. Of course, there's always some overfitting when you use the validation data to tune your parameters, but it will rarely be something that will invalidate your model. It's usually a very, very small overfitting that will not break everything. So, okay, here we split the data. Very, very simple. Split by date is what you need to understand. Third step. Here we will set up a one-step target. And you may be asking, okay, Mario, but what if I want to predict more than one step? And at the end of this, we will see how to do it. But let's start with a one-step target so that we can more easily understand what we are doing here. Then we can expand it to more steps. So the first thing we need to do is actually group our data by product code and actually shift backward the target variable that we want. So here I'm trying to predict the next week sales value. So I will group by product code and actually take the value of the next week that we know in the training data, in the historical data, and actually move it one line back so that I can use it in a machine learning model as the y variable, as the target variable. So how does this look? Here I'm selecting product code 1 so that it's more clear. So you see here we have data for product code 1, for week 0, 1, 2, 3, 4, we have for all the weeks that we selected. And this code simply creates this column, which takes whatever is the next value and aligns it to the previous row. I like to do it this way. I learned it from a very good Russian friend because it makes it much easier for us to compute the features. If we chose instead to actually shift the features forward instead of, let's say, the target variable backward, we would need to shift every feature. But this way we can actually compute the features in the same row without having to deal with realignment of panda cities and get all confused. So here, just understand, we are doing this, we are shifting backward the target value that we want to predict. Oh, but what if I want to predict the sales 4 weeks from now? You just shift the sales 4 weeks from now. For example, here we are simulating being in week 0, let's say. So 1, 2, 3, 4. This value would be 13. Here you would be putting a -4. Okay? Very, very simple. There is no complexity here that you have to add. And of course, we need to do the same to our validation data. So here we use the same function, but applied to the validation data frame. And here is one of these cases where you can easily do some bad data leakage, do some bad things if you don't split before. So after we do this, of course, for the training data, in the last week of our training data, which is week 39, we don't have the sales for next week. Actually, we have it in the historical data, but it is from our validation data set. In this case, for the training, I will just drop these rows. We will not need to use it. In the validation data, we are actually going to use it to see how we can predict for completely new data that we are not using to train or validate. So as you can see, after we drop the NAs, we have the last week as the week 38, as we have the data. The sales next week is referenced to week 39. So now that we have a train and validation data set, we have a target, it's time to create our features. And there are 4 fundamental features for time series that I highly, highly recommend that you always try in your models. It is not very usual that you can say always try something in machine learning, but this is one of these cases. And these are not new features. They have been used in other more non-machine learning traditional time series models. The first one is the lag. It's the classic. It's basically some period before the one that we are predicting. So here I'm going to use the lag 1. So I am just grouping by product code, taking the sales column, which is the, let's say we are on week 0 trying to predict week 1. So we have the value of sales today. I want a feature that is the value of sales last week. So this is very simple. If we look here, we actually have the lag sales. Of course, for week 0, we have no feature, we have no value. When we are trying to predict on week 1, we will use as the lag of sales for that week, the week before it, the week 0, so 11, you can see it is here aligned. Here there are two things that we need to talk about. You have to know if you have the value for this week. So for example, let's say that my model will run every Saturday at 11:59 p.m. So I will have all the data from the current week that I just finished when I try to predict the next week. Okay, so we can use this data. But let's say you are trying on a Wednesday to predict the sales for the next week. So you clearly don't have the full picture of the sales this week. So you will not have this number in your true data. You may have it on historical data, but you will not have on the true data. So you have to take this into consideration and only use numbers that you will have at the time of your prediction. So I'm telling this because this could be considered a lag if we are doing this at Saturday 11:59 p.m. And this then would be the lag of the current week. So it will be a lag too, but this is just an observation. Okay, so this is the first feature that really you have to try. It is, if you want to see it in a more beautiful name, let's say it is an autoregressive model. So it will regress new values over the past series values. So it is the basic model of time series forecasting. And you do this very simply with the group by function on the sales column, and you shift it by one step. See, remember that we were shifting by -1. So now we are shifting forward. So we are getting the last row to align with the next row, okay? Because now we are talking about features and not the target. The second feature that I believe it is very, very important is the difference. So instead of us just having a lag, the absolute, not a mathematical absolute, but the raw value of the series in the last period, we can compute the difference between the current value and the last value. So in this case, again, we have to take into account what data we have at this moment. Right now, we are simulating this scenario where we are predicting at 11:59 p.m. on Saturday. So we have this number. So the difference is simply taking the number of the current row minus the number of the last row in the same column. Here, of course, 12 minus 11 is 1, 10 minus 12 is -2. This is very important in series where changes are more important than necessarily the stability of having the same values as before. So again, it is something you have to try and see if it works well in the case that you are trying to solve for, but it is a very, very good feature for you to try. It is the second most important for me that I try in the time series models and that I recommend that you try. Again, we do the same thing, but for the validation dataset. And the third feature that I really like to try are some rolling statistics. So we can take the mean, the maximum, the minimum, and the standard deviation. I put it in the order that I usually find it more useful. So usually the mean value of the last n period. So for example, you see here that we use the mean value of the last 4 weeks. And I will explain to you this code very soon. So it is what we know as moving average sometimes, knowing that it was that a product sold a lot last week. So for example, taking the maximum of the last 4 weeks, maximum value of sales in the last 4 weeks can be very useful to predict that we will see a dip in the sales this week. So always think about it as rolling statistics that you can compute over your data. So instead of talking about shifting or taking the difference from one value of our time series, Here now we are talking about aggregating some values in a given window in our time series. So here we are doing the same thing. The only difference is that instead of using a function directly, Pandas has this API where you select first the rolling period. So you set this dot rolling and select here the number of rows that you wanted to set the window. It will do a sliding window over the rows and of course the column that you select. And then you can compute different functions over it. You can pass some custom functions here, but they have this optimized default functions like min, max, minimum, etc. So here there is a peculiarity of Pandas that when you do this rolling, it actually returns to you a series with two indices. So we have an index with two columns actually. One is the product code and the second one is the row number. So to actually align it well, to align like we have been doing with our data, we need to have an index that is the same index as our original data frame, our melt train data frame. So here we need to use this reset index function. So we just tell Pandas to drop the level 0 of the index. So drop the first of these two columns of the index, and it will return to us a series with the right index, the index of each row. And if we look, we can do the same code that we can use the same code, do the same process that we have been doing. So here I have the rolling for.min.reset index to drop the product code, and actually I can align it very well with my original data frame. This is a Pandas peculiarity. The most important thing here is that you understand that this is a rolling statistic. So just for us to make sure, here you see we don't have for the three first rows, of course, we don't have the data for these rows. Some people will recommend that you compute, for example, for if you don't have the last 4 rows, you compute for as many rows as you have. I don't see a big difference in practice of doing this. I never saw a big performance difference because of this. So having name values here is completely fine in most cases, I guess. So what are we doing here? Here we are computing the average of these 4 rows. We have 41 divided by 4, 10.25. Just to make it very clear, it's just an average, and then we jump 1 row and actually take 12, 10, 8, 13. So remember, we are always computing with the same row. If we did not have this value, for example, the value for the current week, we would do a shift by -2 here, in the sales next week, so that we can account for the gap in the data that we have, that we don't have the data for the current week. But here, again, to understand it, we are predicting at 11:59 p.m. on a Saturday, so we have this data. And we do the same thing, exact same function, but applied to the validation data frame, the validation data set. And the fourth and last fundamental feature that I try to compute when I have time series is what I call a date component. So this is very important for us to capture the seasonality in the data. So capturing some anomalies that we may see because of the point in time that we are. For example, Black Friday usually has different patterns of selling than the other days of the year. Unfortunately, it's not available in this data set. So here we don't have the true dates. We just have the number of the week. But if we had it, I would compute features like the day of the week, the day of year, the month, the day of month. And you can even go forward and actually put holidays and special promotion days since a new store opened. There are many things that you can add here, but what I want you to leave here today knowing is that you should create features that are date components. Simply a feature, a column, let's say, telling that today is day 0 of the week, it's Sunday, or it's day 1, Monday, and a tree model like we are doing here today will be able to capture the seasonality based on this. If we are talking about linear models, you can just one hot encode it and it will capture the same way. So as an extra tip, I want you to think about interactions. So we could very well do something like taking the sales of this week minus the average 4-week sale value. And actually, this can be a good feature. So think about interactions that you can do between these these three types of features. Actually, does not make much sense to subtract the sales value from the day of the week. But from the three other feature types that we saw, you can actually do some interactions, and they may be pretty good sometimes. About the interactions, usually the one that works better for me is doing some subtraction. So in this case, I'm giving the example of the lag minus a rolling statistic. The other type of interaction that usually works well for me is some kind of ratio. So let's say that we take the rolling average of the last 4 weeks of sales divided by the rolling standard deviation of these 4 weeks. So we have some kind of normalization going on. We could actually take the sales value for the last week for the lag divided by the standard deviation minus, or do the normalization minus the mean divided by the standard deviation. There are many interactions that you can try, and I just want for you to keep this in mind when you are trying to improve this model. So in step 5, after we created our features, it's time for us to choose an evaluation metric. The most popular evaluation metric for forecasting in general is mean absolute percentage error. This is basically the true value minus the predicted value divided by the true value, and the absolute, you take the absolute of this quantity and then you take the mean over all your examples. It is very good, very popular because it's easy to understand. But there is one problem. When our true value is 0, we actually have a division by 0, and this is terrible. So how can we fix this? There is an alternative, WMAPE, which is the weighted mean absolute percentage error. In this case, instead of doing the average and doing the division before taking the average, we actually take the difference between the actual value and the predicted value. Then we take the absolute sum all these values and divide by the total sum of the absolute values of the true amounts that we are trying to predict. This way, if we have at least one value that's not 0, we can do the division. So I would say this is the second most popular way of measuring this error. There are more advanced ways, but these are good because it's easy to interpret, it's easy to explain to non-technical people what we are trying to measure. And usually people have already seen or tried to understand percentages in another context, so it makes our life much easier. So these are the two metrics that I will use here. I usually don't like to choose only one metric. I try to choose between 2 and 3, because this way you can actually have different points of view of what your model is doing. So let's say we were in a general regression setting. I would choose at least the mean absolute error and a squared error, the root mean squared error, for example, because I would like to see how my model is doing, both close to the median and both when I have the extreme values. So the squared error would show me one side of my model and the mean absolute error would show another side. So I'm telling you this because my recommendation is that you actually use at least 2, but no more than 3 metrics to check different ways that your model is actually working in the data. So to do this in the code, we actually create the function, very simple. First argument is an array or a panda series with the true values. Second one is another array or series with some predictions. This can come from the model or some other source, like we will see in the next step. So first I calculate the absolute percentage error, and it's that formula but implemented here. And some softwares that you see around will do something that's very questionable when they find some zero. They will actually say that if it can't divide, so if the true value is zero, it can't do the division, the error is zero. I think this is very questionable because it can give you a very optimistic view of the performance of your model. So I would rather be pleasantly surprised by the performance of my model than actually think that it is performing much better than it actually will when I deploy it in production. So I use this function called numpy is finite. It will create a true-false mask over all the values, telling if the value is computable, so if it's not nan or infinite or some weird value. Then I take the tilde, so I take the no, the not this. So not finite is where we will set the error to 1, which would be 100%. So I'm telling, okay, for every data point that you can't calculate the error, I will assume that the error is 100%, so it's pretty bad. And then we do the mean over these values. I left this here so that you can actually uncomment and see the difference if you would like to calculate with this zero rule, let's say. And there is the function to calculate the WMAP, which takes the same arguments, but this time we are doing the other formula. Here we don't need to make any adjustments. We just calculate the absolute value of the differences, sum them all, and then divide by the sum of the absolute values of the true amounts we are trying to predict. Next step, we need to establish baseline. How do we know that our model is good? It does not make sense to implement a machine learning model that has some complexity if it will not improve over some simple rule, some simple baseline. If the company that you are working for already has some forecasting system, so you should calculate the MAP or whatever error you decide to use over the same data, but using the previous model, the previous forecasting system, so that you have a baseline. We need to improve over this baseline. We need to create a model that's better than what is already working. Sometimes we don't have a baseline, so we don't have a current system. In this case, I like to put some very naive baselines. If it's the first model that I'm creating for some company or for some system, I like to use a very naive but very useful and strong baseline, which is predicting that the next period, in this case, our data is weekly, so it's the next week, but the next period will be equal, the value of the next period will be equal to the current value, to the value for the current period. So if we were talking about stock prices, I would predict that tomorrow the stock price will be the same as today, or tomorrow the stock return will be the same as it was today. This is a very strong baseline. Sometimes you see other baselines like using 0 as a prediction for everything. It depends on the case, but this one will actually be pretty good, pretty strong. If you can beat this baseline, you can be very confident that your model will perform well in production. So how we do it? We already have these values. So in the melt train, all the melt data frames, we have the sales column, which are the sales for the current week. We will set it as our predictions, and we set the y true as the sales of next week, which is our true y value. So if we do the mean absolute percentage error over it, we get 67%. If we do the weighted version of it, we get about 31%. In practice, usually I look for 30% forecast error at the start, at a minimum. This is usually a good indication that we can improve over it and actually make something useful, because 30% is usually too high for it to be practical, for it to be useful for most cases. But what I like to call to your attention here is always take into account the error in the context that you are predicting. So in this case, a lot of the targets that we have here sold less than 10 units. So if we think about it, if we predicted that we would sell 3 units and actually sold 2, we have 50% error. But it's not terrible from a practical standpoint. So a 50% error in this case would not be terrible. But if we predicted that we would sell 3,000 units and actually sold 2,000, yes, this would be very bad. So always take into account the context of your prediction, the amount, the quantity of the product that you are predicting, so that you can have a better idea of how much you can, of what error will be useful in practice. So now we get to the part where we train the model. We have our features, a baseline, a metric. Right now our data frame has the sales of the current week, the Y value, which are the sales of the next week, and we have the features, the lag, the difference, and the rolling average of the last 4 weeks. Here we see everything as NaN because we are seeing only the first week of every product. It's sorted first by product here, so everything is NaN for these variables in the first week. As I said, this is usually not a problem. We will have an imputer. So we have to select some features. I like to create a list with the features I want to use in the model. So I'm going to use, like I said, we are simulating being in a Saturday, 11:59 p.m. So we have the value of the sales this week. If we take this out, there is no problem. We have to use whatever we have as features. And I get the other three that we computed. So like I said, I will use a simple imputer. This is just taking the average of each column, and where it finds a NaN value, it will replace it by the value of the average of the the current column. So we get this object from Scikit-Learn. We run the fit transform method so that we can actually fit the imputer, get the averages, and actually return to us this melt train only with the selected features. So here I'm passing the list with the names of the features, and this will be our X train. And the Y train will be just this sales next week column that we have in the melt train. Then we simply get the usual Scikit-Learn routine. We get a random forest. I don't like to make random forests with less than 100 trees. Usually the more the better. And just setting a random state, and I have 6 cores, so I'm using them to train, fitting the model to the XTR and YTR that we have. So step 8, of course, is evaluating the model. Did we beat the baseline? Here we just need to impute the data for the validation dataset, so melt valid. So we pass melt valid with the list of features here to the transform method of the fitted imputer to create our XVol. And for the YVol, we are going to use the sales next week, and we do the prediction. Nothing new here, just Scikit-Learn. So the mean absolute percentage error was 64, before 65 if we round it up. So before it was 6-7%, so we have an improvement, not a big improvement, but some improvement. And the WMAP is 30%, it was before 31% by rounding. So it's not a big improvement, but I like that a very simple model, a first model, is already showing some improvement. So we can still improve this model with more features. It's very, very unusual that a model will be able to strongly beat a baseline just by using lag 1, difference 1, and a simple rolling average of 4 periods. Usually we have to compute other features, and when I mean other features, are the same types of features but for more periods, so that we can improve the model and actually extract all the value, all the information that is in the series. So a question I got a lot after I wrote the article about this method was, how can I extend this to predict more than one step, more than 1 week? And here I will show you how to do it. First thing, we need to actually create the column. So I will create here a second Y variable, so it will be sales next week. A very, very good name, as you can notice, and we simply create a new column where we shift by -2 the amount of sales that we had for that product. Same thing as before, but now with -2 and a different name. So if we look at our data, right now we have, for example, for week 0, we have the sales of next week are 12, so 12, it's correct, and the sales of the week after this next week, the next week, is 10, so sales next week is 10 here. So it's just a question of aligning the Y value, the target value that you really want to predict. And like before, we need to drop the NA values on the Y part. So here I am using the same drop NA function, but this time I'm using a subset, this argument, to actually tell it that is only to drop rows that have nans in these two columns. So it will not drop nans, just for example this first row will not be dropped. Otherwise, if we don't send some names in the subset argument, it will drop this just because it has nans in any of the columns. I don't think it would make a big difference, but I just want to be consistent here in our modeling. And again, we get the imputer, we do the melt train, same features, but now our Y variable is not only the sales next week, but we have to pass this list of names of columns. So we have 2 columns in the Y variable. It may be the first time that you see a model that predicts 2 things, let's say, at the same time. This is called multi-output modeling, and it is very, very useful, as you can notice, and a lot of Scikit-Learn models actually do it natively. So we don't have to change anything in our random forest, we just fit it again, but now our Y having 2 variables. So let's see what happened. We do again the same transformation for xvol. Yvol now has to be the 2 columns that we want to predict. So our mean absolute percentage error, it's about the same for the first column, and it is about 68% for the second column. Here, of course, we need to calculate the baseline for this so that we can know if it's good or not, but my goal here is just to show you how to actually do this extension in the model, which is the hard part. And if we calculate the WMAP, we actually get 30% in the first week, so it's the same, and 31% in the second week. Of course, like I said, this can be much improved if we actually go and create new features, try new things, and I will tell you some next steps that I suggest you do if you want to continue learning with this dataset. So another question that is very common is how I use it in production. How do I predict for new examples? And I want you to know that as long as you have the same features you use it to train, you can predict for any period. So here we have our melt valid. Remember that I kept the last rows that we really don't have the data. So we don't have the data for week 52 here. So how we do it in this case? This is just like a real case where we, for example, have the week today that you are watching this workshop, and we want to predict the next week. How we do it? And we just need to compute the features, the same features, but for the current week or the current period. In this case, we already have computed, so we have the lag sales, the diff sales, mean sales, and here you may notice the numbers will not make sense if you look between the rows, because here it is sorted by product. You could even create a list, something like this, 2.0 minus 2.0, 0.5, and I need the first one is the sales. So for example 11, we have 4 features. We just need to pass a list of 4 numbers for the model to predict. Okay, this is just what's happening here. As long as you can compute these features, you can make new predictions. So how we do it? I will get all the samples that are in week 51. So here we have 1 sample for each product. For example, for the first row, it will take sales, leg sales, diff sales, mean sales that we calculated using the methods that I showed you before. And actually, you make the prediction. You get, in this case, we are using the multi-step model, so we get two columns of predictions, one prediction for each row and each of our Ys, the 2 weeks that we are trying to predict. And then, just for fun, I actually set it as new columns here, so you can see if we had some values here, let's say that next week we can go and fill these values with the true data that we collected, and we can compare our prediction to what actually happened in real life, and we can actually see if our model is actually working in new data. These are basically the 10 steps that you need to do. This will give you a model to predict a time series using machine learning, and you just then need to try more features with more periods, so leg 2, leg 3, rolling average of 4, of 5, of 7 weeks, of more periods, differences, adding holidays, maybe even adding characteristics of the items that you are selling, adding weather data. Sometimes in some specific cases it can help. If there was a Walmart competition where we had to predict how sales would be affected by a coming storm around the store, so weather data can help. So it's a question of putting more features, of trying different models, maybe a linear model, maybe even an ensemble of models. One way that you can look for improvements is to find which products have the worst errors. So you store the predictions in your validation data, and you actually go and check which are the products that have the worst absolute percentage error. Which products are the ones that I am making the worst mistakes? And sometimes you can find patterns that will actually tell you the direction to go. This is called error analysis. And of course, you can tune the model and find better parameters, even light GBM, trying a different model, changing the target. So now it's your turn. Go on and apply what you learned here in your dataset and share the results with our community. Let us see how you applied what you learned. And thank you for watching.